All right, so here we are. We've already talked about this slide. So what does that mean? So here's different solids. Notice there are different indexes of refraction. All indexes of refraction for our purposes right now are greater than +1. Air is, we pretty much call that in a vacuum, okay? Because here's stuff that all of our air is made up of. And so it comes out, if we take it out to 3 sig figs, it's pretty much 1.0. We use water a lot, 1.33. And so how does this index of refraction work? First of all, let's go back. Let's go back and law of reflection and refraction. So here's what we got. Coming in, law of reflection. Comes in, angle of incidence equals angle of reflection. Theta I equals theta R. And we use that a lot to derive a bunch of equations in upper optics courses. But for our purposes, that's just a nice thing to know. Okay, and it's also why we have to keep things polished if we want, like our glasses. If they get too much stuff on them, what the fuck? Oh, it's a thermite ball. I was like, what the heck is that? It's ugly. Looked like I had something else on my desk there. And now we're looking at the angle of law of refraction, which basically says this: N of a substance. And what it does, what this does, is equal to c in the speed of light in a vacuum divided by the speed of light in the substance. Okay? Speed of light in the substance. That doesn't mean light slows down. All right? Light still goes at 3.0 times 10 to the 8 meters per second, even when it's inside the substance. The problem is it's stopping at a McDonald's. It's stopping at a bunch of electrons and protons and just hanging out and then moving. It's taking a while for it to get through, to bounce around and to get out of there. Okay? In other words, I can go 60 miles an hour between McDonald's here, between every McDonald's here in Columbia, okay? But it's going to take me hours to get there because I'm stopping at McDonald's all the time. All right? So this is refraction. And what this does, what does refract mean? Refraction bends light. Bends light. All right? And so that's what we're going to talk about here. So here we go. So notice what happens. Now this is where here's Snell's law of refraction. All right. So here's what happened. The incident ray coming in, reflected ray coming out. Notice air has an index of refraction of 1.00. In water, 1.33 is greater than air. So therefore the light bends toward the normal. All right. But notice if I've got the little laser pointer in under the water and I shoot it up, angle of incidence, angle of reflection, notice how this one bends further away from the normal. Theta 2 is greater than theta 1. In this case, theta 2 is less than theta 1. So let me write that out. So it bends light. So here's what you need to know. If I was writing notes, I am writing notes, so that's what the hell I'm going to do. All right, so bends light. So this means the law of refraction looks like this. It's coming in, dotted line coming down. Let's say this N1 is equal to water. Oh, is equal to air. That's air. N2 is equal to water. Coming in like this. Theta 1. This will equal theta 1. And it'll bend towards the normal. So when N1 is less than N2, theta 1 is greater than theta 2. Just the opposite happens if N1 is equal to 1.33. Okay, so we've got the water on top this time. And here's the normal light coming in. And then it bends like this if this is air. Or, yeah, this is air. And N2 is equal to 1.00, theta 1. Bending away from the normal, theta 2. N1 greater than N2, then theta 1 is less than theta 2. And that has a unique consequence. That has something kind of funny happens because of that, because of the nature of that, because of the physical attribute of that. And here's what happens. And it's pretty, and Snell's law, we can in fact, we've done enough. We've done enough. So let's go ahead and do this little Snell's law problem. Then we'll come back, and this is the end of class for today. All right, this is the end of class for today. So we'll start. Well, I'm going to start here in about 15 minutes to do the second class, and then I'm going to leave. But let's go. Let's just go ahead and do this problem right here. So there's a light. This is a good test question. Light strikes an air-water surface at an angle with respect to the normal. Find the angle of refraction when the direction of the ray is A from air to water, and then from water to air. And then tomorrow, we will start with total internal reflection, and then we'll probably be able to jump into lenses or mirrors. We'll do mirrors. And then on Thursday, we'll do lenses and the eyeball. And that will be more than enough stuff. And anything I want to add on the Tuesday we come back for the test, I can still do, because I want you to be up to speed on this. All right? So here we go. So let's just do this problem real fast. And here it is. It is 46 air water 46 degrees. Okay. All right. So, well, I don't need to do it. Yeah, I do. Yeah, I do. Think I'm running out of gas? Oh, maybe. All right, so here we go. Angle of incidence. (46 degrees). All right. This is 1.00, 1.33. So it's going to bend towards the normal. I need to find theta 2. If theta 1 is equal to 46 degrees, and N1 is equal to that, and N2 is equal to that. So I know Snell's law says this. N1 sine theta 1 is equal to N2 sine theta 2. Let's just do the algebra here. So we get N1 sine theta 1 over N2 is equal to sine theta 2. Very critical thing here. This number has to be less than 1. This over here has to be less than or equal to 1, less than 1, because the sine function, remember, fluctuates between -1 and 1. So theta 2 is equal to the inverse sine of N1 sine 1 sine theta 1 over N2. All right, so if you wanted to do that, there it is solved, and the rest is just punching in numbers. And I think the interesting thing that we'll find when we punch in the numbers on this is we'll let them do here for us. Here's what we came up with. So theta 2 is equal to 33 degrees, where for the first scenario, where theta 2 is equal to 74 degrees for this scenario. Right? So, and an interesting thing, if I could get the angle just right, what would happen? And that's where we're going to start tomorrow, is with total internal reflection. Okay, you've been good sports out here.